So anyways, up to this point, we've seen linear search. We've seen that linear search is the best among the best possible algorithms we can obtain for the search problem when we have no information about what exactly, like, is it unsorted and so on. Like, we have a lot of things that we could possibly do from there. So what I'm going to be doing today is we're going to be considering, seeing as we talked about linear search already, and we've seen that it has this lower bound that takes linear time. It requires linear time to solve that problem. What can we do if we know actually more information about our input? So suppose I give you a case where instead of it just being any old array L of n elements, what if the elements are actually sorted? So it means that these elements are comparable, meaning that I can always list them out from smallest to largest. So just as an example, so when we talked about linear search, I talked about these n boxes we had, right? Here are just 5 of them. In here, I didn't necessarily know what I might get when I open up one of these boxes. However, here's an example of an instance that might look like. So suppose in position 0, I have a 2. Position 1, I have a 3. Position 2, I have a 5. Position 3, I have a 6. And position 4, I have a 7. So I have all of them, but notice that the value doesn't like dip down, for example. It always starts from smallest to largest. So they're going to be in non-decreasing order. So I'm just going to say, so we've seen how to solve the search problem. Oh no, my little turtle friend fell. I'll help my turtle friend out in a little bit, okay? We've seen how to solve the search problem in big O of n time. We've seen this with linear search, right? And we also established that that is among the best known algorithms for solving the search problem. This is when the array is unsorted. So instead we're going to assume array L contains n comparable objects or comparable elements. So that means that you should be able to tell me if it's less than that thing, it's equal to the thing, or it is greater than the thing. So if I give you 2 numbers, for example, numbers are comparable objects or comparable elements. There's other kinds that you can have as well. There's many kinds of different kinds of data you can have that have this property. If you could do this, then you could say it's comparable. So anyways, if you know it has n comparable elements and L is sorted in non-decreasing order. Keep in mind this is a rather loose constraint. You can always do the same thing but backwards if you need to. Note that if it's comparable, you could easily just flip these signs and you could change the ordering very easily. I'll let you think about that. So if you have this, do you have to go through the process that we went through before where we didn't know anything what's happening inside of here? No, right? I know that they're in sorted order from smallest to largest. So if I go through the same process I had before, if I just don't know what's in here, if I'm looking for X, sorry, that noise is very satisfying. I don't have to just guess right here and go sweep from left to right. Although that is correct, it most certainly will work. And it'll run in linear time. But normally when we try to solve problems, if we're given additional information like this, let's try to take advantage of that information. So instead of just guessing from here, say guessing sweeping from left to right, maybe we could do something else. So suppose instead of sweeping from left to right, we do something else here. So I have 5 elements in there. Anyways, we have our array L, and we know that they're sorted from smallest to largest in here. Now, like I said, you can always scan from left to right in this array, and you can indeed use linear search to correctly solve whether X is in the array or not. So for example, if I was looking for X is 8, you'll notice that it's not in here. So you'd examine all of them if you're using linear search. But here's another thing. Do you notice that 8 is actually always going to be to the right of 7? Do you see that? Likewise, if I had X, say another problem instance, if I had a 1, notice 1 isn't anywhere in here, but you know that 1 would always be to the left of 2 because it's sorted, right? Likewise, if I was looking for a 4, is it going to be anywhere? Is it going to be over here in the array? No, man, it's not going to be to the left of here. It's going to be somewhere between 3 and 5. That is something we know because it's sorted. So that brings me to the main idea I'm going to present here for you is what we call binary search. So instead of performing our guess here and sweeping from left to right, like we did in linear search, we can do something a little bit smarter here, okay? So instead, suppose that I try to cleave this array, not literally, but figuratively. I would like to have it so that when I make a guess, I should be able to tell you everything to the left of me is less than me, and I may consider going left, or whatever I'm looking for may be bigger than my element, so I have to go right. So instead of it just being where I sweep from the left, maybe I should start in the middle. That may be a good place for me to start. So suppose I start right here. Suppose I make a guess that's right here. So you might ask, Dan, what exactly and where exactly is that? So suppose I have two bounds. I have a lower bound, like 0, and an upper bound guess of n minus 1. Now, suppose that I wanted to guess a position. Suppose I guess L plus U divided by 2. This will be about the middle. So I'm just going to round that down. This is floor. These are floor signs. It means round down. So for example, if you had a number like 2.5, I'm going to say make it a 2. If it's 2.8, make it a 2. If it's 2.9, make it a 2. Okay? That's what the floor means. This is the floor function. So this will give me a middle position. So for example here, if n is 5, then n minus 1 is 4. So that means I could have 0 plus 4 divided by 2. So I have 4 over 2, which is just 2, right? That puts me right here. Likewise, if I had, say, 6 elements, it would be 0 plus 5 divided by 2, which, although I'd have an even number, I would need to pick some side to be the middle, so you'd go to the left of the middle in that case. So notice here, I start here. Notice that this is not 4, right? This does not equal 4. So do I need to go to the right at all? Is there anything over here that might get me 4? I want to know where it is. Nah, man, I don't need any of that. And you're not going to find 4 over there. You may find it over here, though, in this stuff. So notice that I've examined this position. There's no match with 4, so I know this position and anything to its right is out of the question. It's not going to be there. So now, naturally, what should I do? Well, what I could do, quite simply, is just make another guess. So you can think of this like a guessing game. You can use this strategy, by the way, if you think of a number sequence and somebody guesses a number for you, you can use this strategy to improve your guessing game to try to make it so you reduce the number of guesses you make. So if you ever find yourself playing a game of hot or cold, or guess what my number is, and they tell you it's either smaller or bigger, if you use this strategy, you could reduce the number of guesses probably for your strategy. So here we go. So suppose that I did this again. Well, notice that if I try to guess over this, I may guess this one or this one possibly. The point is that once I'm in here, I can check if 4 is there, and I can repeat this process over and over again. So in this case, notice that in here, I would examine this left part, or what we'll call colloquially the left half. In this left half, I would go in there, and I would apply the same process. Now, what I would do is I would apply it over the lower bound. The lower bound still stays 0 because I want that left half. But this changes from n minus 1 to 2, because I already guessed that. But is it really just 2? No, it's not just 2. It's 2 minus 1, because I already examined position 2. There's no reason for me to look at that. So then I look at these two spots, then I make my guess again. So my guess would be right here. 0 plus 1 divided by 2. So I have 1/2. Round that down is just 0. So I guess here next. That's not equal to 4. There's nothing to my left, right? But I don't have to look at this anymore, so I consider my right half. My intervals will change. Notice that now I'm going to bump this up by my guess plus 1, because I'm not going to check this spot again. And then I check it with 1 and 1. So notice that my guess will get me 1 plus 1 divided by 2, which is 2 over 2. That is just 1. That gets me right here. Notice that this is not equal to 4. And thus, what I do is, it's definitely not here, but 4 would be to my right, right? But you'll notice very quickly there's nothing there, right? But the thing is, I'm going to go to my right, so I'm going to make it whatever my guess was, plus 1. So I'm going to make this 2. But notice that these two numbers crisscross over each other. This is supposed to be a lower bound on my guess. This is supposed to be an upper bound on my guess. But notice that the lower bound now exceeds over the upper bound. This is what we call crossing the interval. They cross over each other. This means that there's nothing else left for me to check. And thus, I can tell you right away that 4 is not in this array. And this is what binary search is all about. So it's just playing a guessing game. That's all. The main thing that we're using is the fact that we know that the array is sorted. That's the big thing we're using here. So let's write out what this looks like. And I must stress that this is a very naturally recursive process, where every time I make a guess, notice that every single time I do the same exact thing, except on a smaller subproblem. So this is a very natural thing for me to describe using what we call recursion. So I want to take a problem, I want to solve a smaller part of it, so I describe this process in terms of myself until I get a sufficiently small enough problem that I can easily solve. So that's how I'm going to try to use recursion here. This is what we call a divide and conquer approach. So you can almost see this cutting out, where every time I cleave it, I always discard roughly half. So here we go. So here's the algorithm. So we're going to call it binary search. We're going to have the array L. We're going to have a value X. We're going to have L and U. Now, as I sort of alluded to, actually, what I alluded to earlier, you're going to, when you initially call this, when you start this algorithm, what you do is you would assign L and U as follows. You would assign L to be 0, and you would make U n minus 1. So that's what you would assign initially L and U when you start this process. So I've deliberately written like this, even though it doesn't fit the same problem specifications, because you can easily rewrite this algorithm such that you have what we call a driver function that will call this with those two initial values in there. So there's the input and the output. Make sure you always state this stuff. It's got to be very clear for your reader. We have array L. And I must stress that this is a sorted array, so it means that we're considering a special case of the search problem. We have a value X, lower bound L, upper bound U. So these are lower and upper bounds on our guess. And this time I'm going to make it so it presents you the position. It's a position I such that L sub I is equal to X if X is in L, and minus 1 if X is not in L. So anyways, let's start getting into this. So the first thing did you remember how I stopped this process? So if I don't find the element I'm looking for, I don't find X. Well, this would be happening when the intervals cross, right? When L becomes larger than U, meaning there's no more elements to look at. So if L is greater than U, then we're going to return -1 because there's no more elements to look at. Otherwise, we're going to make our guess like we did over there. We're going to assign mid to be our guess. This can be L plus U divided by 2. We round it down. One tip I can give you about implementation is that if you're doing integer arithmetic, like a lot of programming languages, it will automatically round down for you, such as like Java or C++. At least at this time, those languages would automatically round this down because you're dealing with integer types. You have to be very mindful of this when it comes to languages that don't have typing like that. The difference between integer division versus a regular division might matter, like in Python. If L sub mid, so we're checking position mid in L, and we see if that's equal to X, so I check in that box. If it is the case, then I found it. Otherwise, we have to examine either the left half or the right half. First, let's examine when L sub mid. So our guess currently is less than the current one, meaning that we have to go to the right half. So if this is the case, then we're going to return the result of doing binary search. So we're going to call binary search. So we're going to start this process up again with the following parameters for the inputs. So we're going to use L, as we did before, X again, except we're going to have mid plus 1. So we're going to have the lower bound. We're going to make it to the next position because we already checked our own, right? We know it's not equal to X. And then we have U is remaining unchanged. So that's your right half that you consider. Otherwise, you consider the left half. Otherwise, you return the result of calling binary search on the left half. LX, you would do this on L for the lower bound. We want to use L because we're going to the left half. But we already checked mid, so we're going to move it down by 1 position on the right half. Sorry, the right part of the left half. So this will be going on our left half. This is on our right half, but notice this covers all the cases. So that's binary search, everybody. So with this, the goal is to try to improve the time complexity for the search problem in this special case when the array is sorted. So, what exactly causes this to have worst case behavior? Notice that in this case, sorry, I was pressing on this chest here. It's pretty fun. If I were to go through this, notice that I'm at the mercy of these recursive calls. Notice that you could actually rewrite this algorithm using just purely iteration. So just using a while loop would suffice. But I'll let you think about that. The point is that every time I make a guess, there's a possibility it's not going to be equal to X. So naturally, if I want to make this happen as much as possible, if I want to make it so that there's this maximum number of recursive calls that happen, the worst case is just going to be simply when X is not in L. Akin to something like linear search, but notice that this will cause us to have to go all the way through all of this work until we reach this point. So there's going to be a case where we're going to have not find X and we're going to have nothing else to evaluate. So we want to make it so it takes in as many possible guesses as possible. So we're going to try to bound this. So the first thing you should notice here is that if we're going to measure the time complexity of this, we need to think about analyzing recursive algorithm. Now, before I do that, I want to give you just a motivation behind the correctness of this algorithm. So I must stress that every time you make a guess here, when you make that guess, it's either going to be equal to that, or if it's not equal, you can guarantee it's going to be sitting in some interval. So its position is going to be somewhere between that one or this one. Notice the positioning of those guesses. So if you guess at a certain point, so if I make this number of guesses, notice that every time I do it at a given guess at a spot, If it's not equal, then you can tell me it's either in that one or in this one. Like, that's something you could always say about binary search. If it exists, then it will most certainly eventually get this. If not, it most certainly will return -1. You could prove this directly, but you'll find that the cases are going to get a little bit more muddy. But you can use the idea of invariance. I'll encourage you to think about it, to think about how you would come up with an argument using induction like this. Let's talk about the time complexity. So the big thing is that this is a recursive algorithm, and ultimately I want to know two questions. If I ignore the recursion, how much work is being done here in one call? So how many operations are happening in just one call? And then the other thing is how many calls are going to happen at most in the worst case? So how many calls are happening in one call, and how many times at most are they going to happen? So if I can answer all two pieces of this plus the third, then we're done. So if I ignore the recursion first, this is actually how you could analyze this algorithm. If you ignore the recursion, so you ignore the recursion first, notice that if this takes constant time, that takes constant time. Notice that all of this, I'll let you think about it, takes constant time. So notice that if you take all of this, you could show that this all is, when you ignore the recursion, all of this is just some constant number of operations. So I'll have more details in my notes. But we still have to incorporate the recursion. So for one call of this algorithm, in the worst case, it will be that either it goes to the left half or the right half. So we got right half, left half. Can it do both at the same time? No, right? It only could either do this one or that one. So there's one recursive call at most that can happen, and each one of these calls, there's a constant number of operations. So I'm going to formulate this as a recurrence relation, and we're going to try to find out the asymptotic nature or asymptotic behavior of that complexity function. Once I have that, I have the answer of what the worst case running time of binary search is. So hopefully the game plan is clear. We're going to try to come up with a recurrence relation based on what we just had here. So far we know for each call, one recursive call happens, and each time it's always going to be done on something that's going to be roughly half-ish. We'll see. Plus, every one of the calls does some constant number of operations. So let's put it all together. So here we go. So let's think about how the recursion works here. So I'm going to draw a picture to help us think about this. Okay. So suppose I make a guess. You know it's going to be in the middle here. Now keep in mind there could be more parts to this array. Presume that this is the interval I'm looking at. Suppose I want to know how many operations are happening with respect to this number of elements. So there may be the case that there's no more elements to look at as well. So just keep that in mind. So I'm going to measure it based on how many elements are in my interval when I think about this. So if I currently consider this one, notice that if this is n elements here, how many are over here and how many are over there? Well, let's think about it. If this is n, well, how many elements are left? Well, if that's n and I took away 1 because I already looked at this, we don't want to look at this again. Well, whatever's here, depending on the parity of the length of this interval, it might be even or odd. If it's even, it may be that one side has a little bit more than the other. But if it's odd, they'll have roughly equal size. Either way, it's roughly equal, but in the odd case, you'll notice that it's going to look much more like this picture. But what the point is that this is going to be no more than n minus 1 divided by 2. So notice that if I have this case, notice that if I'm considering the left half or the right half, the number of elements left for me to look at can never exceed n minus 1 over 2. Does everybody see that? So this is going to be an assumption I'm going to make in how I formulate this. So a simplifying assumption I'm going to make so that both halves of the array have the same size. Which is n minus 1 over 2. So what I'm gonna do is I'm gonna call t of n. I'm gonna call my function t. That's gonna be my complexity function. Its input's gonna be n. So I'm gonna let be our complexity function. So we're gonna put everything we talked about together. So some of it I did not write here on the board, so I encourage you to fill in those details, the things we've talked about. So putting it all together, our recurrence relation is as follows. So we're going to formulate a recurrence relation. It's just simply a function that's written in terms of itself. It has what we call a base case. It should remind you of what we talked about recursion over there. It's the same phenomenon, okay? It's just that this is measuring the time complexity of the algorithm. So it's not an algorithm, it's the time complexity of the algorithm based on our analysis. So I have t of n is going to be t of n minus 1 over 2 plus 1 if n is strictly bigger than 0. And we're going to assume that t of 0 is equal to 1. Now, let me just put it all together here for you. There is one recursive call. It's always on one of these two chunks here. This one or that one. So one call happens. This is how many elements you check at most. There's a constant number of operations that happen for each one of the calls. That's it. And t of 0, that's when we have no more elements. That's when your intervals cross over. And there's a constant number of operations that happen there. So this is our recurrence relation. That's going to represent the time complexity for binary search. Now, I must stress that if you really are nitpick about me using ones here, you can always relabel these with constants as per how I did previously with something like linear search. So now that I have this, I'm going to apply a technique called iterative substitution or repeated substitution to try to solve the recurrence relation. Now, when I say solve, what I'm saying is I want to express this function without any of the recursive parts in it. So I need to find a pattern to make this work. So I'm going to say, let us solve. I'm going to put solve in quotation marks, t of n, by repeated substitution to figure out the time complexity. So now you might ask, what is repeated substitution? Well, what it is we're just going to simply try to observe a pattern that we can check, by the way. If we want to use mathematical induction, we can check if this is indeed going to match what we get from this recurrence relation. I'm not going to do that here for the purposes of time. But what we do is we try to expand out the recursive part of this part right here. Remember, it's expressed in terms of itself. So t of n is expressed with itself in it, right? Until it eventually gets small enough. What my point is that we're going to have this where I want to know how many times can I rewrite this equation But I want to figure out two things. What's happening with the non-recursive work, the stuff that happens other than the recursive call, and what happens, how many times do I have to apply this right here, this recursive call? This is analogous to me performing the recursive case of that recursive algorithm over there. So every time I do this, I want to see how much work gets accrued until I reach the base case, right here for t of 0. So I need to do this. I'm going to keep writing out equations and find out how many equations I need to get to the base case. Once I have this, I'm going to try to tally up all, or almost like I'm collecting it up in a bin, all that non-recursive work, and see how much in total I have at the end of the day. And that'll tell us time complexity. So here we go. So I'm going to expand out this recurrence relation by writing out a new equation for each recursive part. We're going to try to guess a pattern. You would check this with induction if we needed it. But the idea is we're going to try to figure out how many ones I have to write out here. That's all the stuff, all the work I do each time I do a recursive call. So first I have t of n. Well, that's t of n minus 1 over 2 plus 1, right? What I'm going to do is I'm going to write this right here as a new equation. But wherever I have this as the input, I'm going to write that almost like I wrote n right here. So if this was a banana, I would write banana minus 1 over 2. So this is now the banana. Now I'm going to have to write the banana here where it's banana minus 1 over 2. So watch this. So I'm going to have t of n minus 1 over 2 minus 1 over 2. So I just write whatever the input is where it is. Plus 1. Well, what's this? Well, let me rewrite this a little bit because it looks a little bit funky here. Well, this is just t of n minus 1 minus 2 over 2 squared. So I'm going to end up with an extra 2 that gets dragged down. As a result, I'm going to end up with one of these numbers bumping up to a power of 2. At least it looks like that. Plus 1. I'm going to encourage you to try fiddling around with this. It's t of n minus 2 to the power of 0 minus 2 to the power of 1 over 2 squared plus 1. Now, what you could do is you could take this recursive part, write out a new equation for that. So t of n minus 2 to the power of 0 minus 2 to the power of 1 over 2 squared. Once you see this, you're going to start seeing the pattern we might guess. So when I do this, I'm going to write out whatever this is as the input. Now I would go through the same process that I just did, where I would write this here, but you're going to notice it's going to actually create something very similar to this, but it's going to introduce another power of 2 in similar places. So I end up with n minus 2 to the power of 0 minus 2 to the power of 1 minus 2 squared all over 2 cubed plus 1. So there's something interesting going on here. Does everybody see it? So notice that here I had 2 to the power of 1. Now it's 2 to the power of 2. And notice the denominator now has an extra power of 2. Do you see that if I were to apply this equation one more time, like if I take this and rewrite out that, you'll notice it should remind you a lot of the previous one, except it's going to have another power of 2. So it's going to be like 2 to the power of 0 minus 2 to the power of 1 minus 2 to the power of 2 minus the next power. So 2 to the power of 3 divided by 2 to the power of 4. Right? So you see how this is starting to form a pattern here. It's not very clear at first. We have to write it in a very specific way to help us see it. But you can keep writing this out. And this is my guess of what this would look like for an arbitrary application of this equation. So here's my guess. But please take note of how many equations I'm writing down. So I started off with just t of n, but when I did one recursive call, it's just n minus 1 over 2. And then it bumps up by 1, then it bumps up to 2, then bumps up to 3. So notice that every single time I apply this, it goes up by each successive power of 2 in the denominator. So it starts at 2 to the power of 1, 2 squared, 2 cubed. So naturally, the next one would be 2 to the power of 4. So here's the idea of what my guess would look like. So I have n minus 2 to the power of 1 minus 2 squared, sorry, 2 to the power of 1, all the way up to 2 to the power of j. So you know if it's j here, then it's going to be j plus 1 down here. 2 to the power of j plus 1. This will be equal to t of n minus 2 to the power of 0 minus 2 to the power of 1 minus all the way to 2 to the power of j plus 1. So every time I introduce another power of 2, right? And then the exponent down here always goes up by 1. That's my guess. And you add 1 for the non-recursive work, right? So I have a whole bunch of equations here. So notice that there's two things. First thing is notice that the value of this always decreases. It always gets smaller. It never gets bigger. It gets smaller every time I write out a new equation. The other thing is I want to know what happens when we get to t of 0. So notice the input value given to t on the left-hand side decreases with each new equation. So we stop this process when we reach t of 0, right? We stop this process when n minus 2 to the power of 0 minus 2 to the power of 1 minus all the way up to minus 2 to the power of j plus 1 all over 2 to the power of j plus 2. This is after the invocation of this. So notice I'm looking at the right-hand side right now. I want when this is equal to 0 because then whatever this would be that is a sign t of 0 plus 1. And that would cease the recursive part. So I'm going to put star right here because this is going to be a very helpful equation for us. Then, now I'm going to take into consideration how many equations I wrote down. So what would happen in this case is I would have a whole bunch of 1s that I would add up. And then I would have this invocation at this time. T of n minus 2 to the power of 0 minus 2 to the power of 1 all the way up to 2 to the power of j plus 1 divided by 2 to the power of j plus 2 plus 1. So there's a whole bunch of 1s. So this is what t of n is going to be equal to. It's going to be equal to this. So now, what can we do? Well, I'm going to rewrite. So now we want when this is equal to 0, right? So the input of that recursive call. So this is going to be equal to 1 plus 1 all the way up to when this becomes t of 0 plus 1. But you might ask, Dan, how many equations did you write out? Well, let me rewrite this a little bit more carefully. So I'm going to pull that 1 out of there. And let's think about it. Just think about it. Okay. How many equations have I written down? Well, I had j plus 1 many. Notice that the number for that exponent in the bottom actually tells you how many equations you actually wrote out. So it's j plus 1 here. So that means that there's j plus 1 many 1s plus 1 extra 1 I just grabbed from right here. So there's j plus 2 many 1s here right here. Well, what does that mean? Well, this is t of n is equal to j plus 2 plus 1. Now you might be saying, Dan, why don't you just make it j plus 3? You'll see in a moment why I'm not going to do that. You can, but you'll see that this is actually going to be quite nice for us. So now I have actually an equation that connects n up to j, and I would like to know what j is up to. So now we have an equation for t of n. Notice there's nothing involving recursion on that. Now I just need to know what j is. So what is j in relation to all this stuff? Okay, we're almost there. We're almost there. It's a little bit more of a casual day, you see. So anyways, well, we know, so to determine, sorry, there's a mosquito coming after me. They're coming for the juicy, juicy M word, the mayonnaise and mustard, you know, that math. To determine, mosquito, go over there, go over there. To determine the value, out of the way, mosquito, go over there. To determine the value for j, we can use star, right? So notice that in the denominator of star, we had 2 to the power of j plus 2, but we had it so it's equal to 0. So if you multiply both sides by 2 to the power of j plus 2, it just goes away. So now we have n is equal to 2 to the power of 0 plus 2 to the power of 1 plus all the way up to 2 to the power of j plus 1. Which this, if you actually rewrite this is actually a finite series. To the power of I is equal to 0 to j plus 1. So if I gotta rewrite it like this, and naturally, you might look at this and say, Dan, I might know what that series looks like. That's a geometric series. It's a finite geometric series. This is a finite geometric series. Right? So if you're familiar with the geometric series, it has a radius or like that. Sorry, it's the rate. I'm not going to get too overly technical with the geometric series here. It has a fancy name. So I'm going to call that r. It's r is 2 in this case. So you'd see it's r to the I. Now it actually has a closed form if you recognize this. So this right here, so n is equal to this to the power of j plus 1. Now I'm just going to put in this closed form. It's 2 to the power of 0 minus 2 to the power of j plus 2. It always just goes one higher over 1 minus 2, which this is just 2 to the power of j plus 2 minus 1. So I'm going to let you think about how you would formulate this. If you're not sure of the steps here, feel free to ask me about them. I'm very happy to help. Then, now, I'm going to move this minus 1 over to this side. So I have n plus 1 is equal to 2 to the power of j plus 2. And now, when you have something with an exponent like this, and I want to know what j is in relation to n, I'm going to try to get it so j is in somewhere I could rewrite it in a nice way. So watch this. So we're going to move minus 1 to the left-hand side. Then apply logarithms to both sides. And we end up with log base 2 of n plus 1 is equal to log base 2 of 2 to the power of j plus 2. But if you look at this, you see that this is log base 2 of exponent. Well, there's a power rule or power law of logarithms that allows you to pull this exponent out front. Log base 2 of 2 is just 1. Because 2 to the power of what is equal to 2? Just 1. So this ends up just being j plus 2. But here's the thing. We've established that t of n is just j plus 2 plus 1, right? So I'm just going to put in where we had j plus 2, I'm going to put in log base 2 of n plus 1. Therefore, t of n is just log base 2 of n plus 1 plus 1. But if you know your big O, you know that this is big O of log n, which this establishes the time complexity for binary search. So notice that log n is actually much better than linear. So if you know your array is sorted, or you're working with comparable elements and your elements are sorted, if you want to be even more specific, you can use binary search, which is a considerable improvement on linear search.